Thank you all for coming this evening. And it's really nice that we're able to do this virtually, that we don't have to drive on streets that are supposed to ice over later tonight. So that's about the only benefit I know of COVID. COVID was what forced us to have virtual meetings because we couldn't have them physically for a couple of years. And that turned out to be a blessing in disguise for times like now. It also quite widely broadened our membership base. We have members now from, not only in the United States, but we've got people in Canada and Australia and Europe also that are members now. But most of us live right inside the greater Washington, D.C. area. And we're blessed with severe light pollution. We've got limited horizons. We have high humidity. Thanks to our neighbors to the north and to the west, we get periodic smoke particles in the jet stream that travel all the way from Canada and California. So it makes it pretty tough to do observing in and around Washington, D.C. And up until a few years ago, pretty much to survive, you had to have many thousands of dollars worth of specialized filters and monochromatic cameras and this sort of thing, and a huge learning curve to do any observing. And that limited itself to a very small, very specialized, very skilled group of observers. And then the rest of us just had to drive an hour or two west of town or south of town or someplace just to get away to be able to see anything. So what I'll do now is just kind of take you through the experience I had as an early adopter of a Kickstarter program. And I sponsored an EAA program that was on Kickstarter from Unistellar. That's the name of the company. It's founded in Marseille, France, a number of years ago. And I got this telescope. It arrived, and the very first time I used it, in my initial experience, it went from taking it out of the box, and in less than 10 minutes, I was set up and actually observing a nebula. And that really got my attention. That was just an incredible experience. And basically, I just took the iPod, I put everything in a backpack that came with the setup. It was a tripod and the telescope. You can see it there in the picture sitting on the sidewalk in front of my house. Level the tripod, put the scope in a cup on the top, press the on button, connected up an iPhone to the eVscope's Wi-Fi access point, and I launched the Unistellar app that I downloaded from the App Store. And it gave me a choice of it said to slew to some stars and to adjust the focus. So I used the app, the iPhone app, and just used my finger like a little joystick and moved the end of the telescope around to about 45 degrees where I could see some stars on the screen that were out of focus. And the only thing you can adjust on the telescope was a knob on the back right at the bottom. And the telescope came with part of the lens cover, a batten-off mask. So I put the batten-off mask on the end, adjusted it until the vertical line bisected the X that you can see there to the right, and took the batten-off mask off. And then I picked an object from an objects available list that it had. Then I watched the scope slew and center on the object and started observing. All of that took 10 minutes. And it takes less than that most of the time afterwards. So that was amazing. I'm still amazed years after it. So after it's moved over and I started observing, I could just see a lot of stars that it was just collecting, in real time with a Sony camera that's embedded in the scope, which is a Newtonian scope. And I had it look at the Orion Nebula, and also had it look at the Hercules cluster. And when it was aimed at the cluster, you just touch a button on the phone screen, and it starts taking sub-exposures. And that's what they call enhance mode. And then that's just the magic. All of a sudden, instead of seeing a very dim, barely visible object there, or in some cases you can't see an object at all you just see is a dark screen, just it emerges before your eyes, and usually within half a minute to 3 or 4 minutes, you start seeing the object. And that's the beauty in these EAA scopes and smart scopes. And so in 4 minutes, I started seeing this globular cluster quite clearly. And what was happening, the telescope was taking capturing an image from the sensor every 4 seconds. So it's getting 15 images a minute. And every time it got an image, it would send it internally to the side of the telescope that had embedded in it a Raspberry Pi computer. If you've never heard of a Raspberry Pi computer, it's just a very small computer that sits on a small PC board, and it has some I/O out connectivity. It has Bluetooth that we don't use with the scope for this particular thing, but it also has Wi-Fi. TCP/IP protocol can run over Wi-Fi to talk to a tablet or an iPhone that can receive TCP/IP. And that's how you communicate with it. And it also gets information from the smartphone or the tablet to help it find objects in the sky. It gets the precise time of day. It gets the latitude and the longitude and the elevation. And that's the information that it uses with a database that's on board inside of the Raspberry Pi's memory that catalogs several thousand celestial objects so that you can go find these things. You don't have to have a connection to the internet. You only have to have a connection to an iPhone that has the database that's local to the phone. I gave a talk a few months back to the Appalachian Society about how they can backpack with telescopes of this family, this one and others that are backpackable. And as most of you know, the Appalachian Trail runs right through Sky Meadows State Park. And people now can take the smaller EAA telescopes with them and do observings while they hike the trail. And if they have a solar panel, they can charge the thing up during the day, if they're camping for a day, and or rig it up so you can have a solar panel in the back of your backpack and have it charge up a power pack, and then do observing at night if you're doing Appalachian trails. So you can take it with you on the airplanes and things like that. So let's just see the results of what we get before we dig into the details of exactly what these devices are. These are some of the very first images that I did when I got this thing in the early days. Here's the Dumbbell Nebula. On the left side is what you see through a traditional optical telescope. If it's, if you've got a pretty decent clear sky and you're out west of town at like Sky Meadows. If you're inside the DC Beltway, get rid of all but 2 or 3 of those stars, and that's what you see. And then when you turn the scope on and you tell it to start collecting photons, and it starts integrating, over time, what you see on the right side is what emerges. And on some of the scopes, or all of them, I guess, they will take some of the metadata and stamp it for you so that you don't have to take notes to the side. It tells you, how long the exposure's for, what the name of it is, what the Messier number is. Like this is the Dumbbell Nebula M27, and there's the the coordinates from where it was observed, which is Sky Meadows. And that was September the 16th in 2023 that I did this particular one. And then here's some others, just examples of what you get, both things that I've done and things that other people have done. Here's a M42, the Great Nebula in Orion, which is one of the most popular objects up there. You can see Orion's belt, the 3 stars there in the middle. And here's what you get in 44 minutes. And you don't even see this at all inside the Beltway. With binoculars, you can see a little bit of it. You can't see anything nearly like this. This was back in March of 2022, one of the earlier images that I got with the scope. And here's what some other people have done with the same type of telescope. This is with one of the Unistellar ones. That mine was with the Unistellar. Here's one taken with the SeeStar S50 that I did earlier this year. So the difference between this one and this one is the difference between these 2 EAA telescopes. This one is 44 minutes. This is 68 minutes. So going in another 20 minutes with the SeeStar out at Sky Meadows netted this particular one. And then someone, Christian Destinefo over in Europe, was at a dark spot, and he used a SeeStar S50, and here's the Orion Nebula. And they're the same if you look at them really closely. Look at the difference. And this is with a $495 telescope that weighs about, 7 pounds. And what he did in this situation, instead of letting the Raspberry Pi gather up the images and stack them, is he just dumped the images out after he finished his observing session with a USB cable into his laptop, and then he used either Serial or other, gosh, what is it? Blanking on the name. I'll think of it in a minute. The PixelNet or whatever it is.
PixInsight.
What was it?
PixInsight?
Yeah, PixInsight. There you go. Thanks. Yeah, PixInsight. I had a blank moment. Yeah, it's shouldn't have used it enough. Yeah, PixInsight, and use the software there that is very specifically designed, has a tremendous learning curve for it, but you can suss out images like this. So these things, even though they're $500 telescopes, they're apochromatic telescopes. This one has to be an apochromatic refractor. We'll look at technical details in more depth later in this talk. Here's M51, 14 minutes out at Sky Meadows, the Whirlpool Galaxy. It's one that I took. And here's the S50 of M51 that Mattia Pesecchia using PixInsight and using raw images. So these are the two extremes there. They're both pretty decent. A couple of different scopes. Here's the double cluster. And you can see the color in this. Ben Robbins did this, and I think he used Serial for this one. This was with an S50. And here's the Helix Nebulae, also known as the Eye of God. And this was with an Equinox 2. I took this out at Sky Meadows. And we had some supermoons in the recent months. And I took an S30 and set it up on my front porch in Falls Church. I'm about a mile east of the Beltway, right off Route 29. I'm right between Route 29 and Route 50 in Falls Church. And there's a street light about 30 feet from my porch blaring away. And I got this picture of the moon. The moon's got plenty of brightness, so it can overcome, the trashing out of the light. But this isn't with any particular filters, to try and filter anything. This is just a raw image right out of the telescope. So it's pretty amazing what these things can do. And rather than go through all of the Messier objects, I'll just show you Ray Young's capture collection. I never took the time to do it up in a test sheet like he did, but he put together a bunch of images of the objects that he did with his Unistellar EV Scope 2 back in the early days before the version 2 came out. So it gives you an idea of the space objects that you can get with these types of telescopes. So you're not going to get the really teeny tiny stuff that you need, 2 and 3 and 4,000 millimeters of focal length. But for the things that, are within about 1,300 millimeters of refractor focal length and down, namely the Messier objects, the faint fuzzies that are up there, it's really ideal for that. And of course, Andromeda, you can see Andromeda in the first column, down about row number 4. So let's talk about the story behind the electronic assisted astronomy. And what we're going to do is gallop across centuries of relevant discoveries of what set the basis for these telescopes to occur. And we're going to take a little side trip in history of science and kind of human nature about how people react to discoveries, which I find incredibly interesting. And I'll tell you some stories about what happened even in NOVAC regarding the introduction of these telescopes. So if we just go back and really go way, way back, pretty much innovation has been based even before, but one anchor point we can take is mathematics. 3,000 years ago, we started getting arithmetic and geometry and algebra, and the Babylonians brought down calculus in the late 17th century. And then statistics showed up in the 1662, around, and there's the date given for that in Wikipedia. And then the Turing machine, mathematics and algorithms, kind of an approach showed up in the late 30s, etc. So there's lots and lots of stuff in mathematics that sets up a basis for innovation. And all of that led to ancillary notable inventions, the innovations. The first optical telescope lens was attributed to Hans Lippershey in 1608. Pretty simple thing in the Netherlands. And then Galileo developed the first telescope, a couple of lenses at the end of a tube in 1609, and that was in Italy. So what happened when Galileo did that? Well, he met technology resistance, and we still meet technology resistance. So the first thing he did was very gently publish the dialogue concerning the two chief world systems, the Ptolemaic and the Copernican, and so that he could gain favor with the people that had the power, he dedicated it to Pope Urban VIII. And even though he dedicated it and he tried to walk gently, his ideas were considered heretical, and he was called to appear before the Inquisition in Rome in 1633. In the deal that he struck, plea bargaining way back then, he was sentenced to house arrest, where he continued his work and write until he died in 1642. So that's what happened to him in a nutshell. And there's plenty of things on streaming media and then on YouTube and those various sources where you can find out more about Galileo, and lots of nice books to read. It's a fascinating story, and and how he moved us forward, but he didn't do it without being put under house arrest and having his books banned and getting considered a heretic. If we go on further, there's the invention of longitude, John Harrison's clocks back in 1759. There's a fantastic story behind that. The British government was offering a reward equivalent to, probably $1.5 or $2 million in today's dollars if someone could figure out how to measure longitude. We were pretty good with latitude because we had sextants, but longitude, no one knew how to measure it. There was a big battle between the physicists and the astronomers, saying, how do you measure this stuff? And everyone was trying to figure out astronomically how to measure longitude, but they didn't have much luck. But John Harrison was basically a carpenter, and he built his initial clocks out of wood and wood gears and things like that. And then he made different iterations of it. And here's one of his early clocks. If you're ever in the UK, if you're in London, take the London Tube over to Canary Wharf, and there you can get on an elevator that takes you down deep into the ground to a tube that was built around the turn of around 1906 or 8 or somewhere around 1900. And you walk through this iron steel tube to the underneath the river, and go over to the side where the clocks are on display in the museum there at Greenwich. That's how you get to Greenwich the easy way. The hard way is to take the train and go clear around and the Thames, and it takes about an hour and a half that way. You could walk the tunnel in about 20 minutes, and it's a lot of people that live in London don't even know it's there, but that's one of those hidden gems if you're traveling over there. And you can see these clocks, and they were laying around in pieces in the basement in the 1900s to 1920, and someone found them and realized that this was what caused the measurement of longitude, and it was time-based, not astronomically based. And since at that time, kind of the center of the world was the United Kingdom and Great Britain, and so the prime meridian was set through Greenwich, and then just the longitude was marked off around the circumference of the Earth, and that's how longitude, which is totally unrelated to latitude, formed our system, for measuring things. And then we did it all with land surveying for years and years and years. And there's an interesting story there is here in the US, we had a way of marking all these things with these things called benchmarks. If you hike around, every now and then you'll see them stuck on the ground, and it'll show you the latitude and longitude. And that's from these different geophysical surveys that have taken place over the years. And what the government did was is they usually hired college kids during the summer to do the surveying. And it's interesting, after as time passed on, the GPS satellites were put into orbit, and we got really good surveying information by making tangential lines down to a make-believe sphere in a tangential line down to the surface, which you can't do with surveying instruments because of the terrain. But they found out that they were about 20 miles off, I think, at 4 corners. and there's all sorts of errors. And the error seems to grow from east to west. And the hypothesis is this is maybe all the bars that they started frequently more and more frequently as all these college kids kept migrating from east to west to do these surveys. And so no one's going back and redoing, where the boundaries are to the states or any of this, but there's a lot of surveying error over the years, and a lot of that got rectified. And probably one of the biggest things that we depend upon now are these GPS satellites for all sorts of everyday stuff. You get in your car now, turn on your guidance system, you don't even know where you're going, and you go there with surety that you're going to reach it there, and it tells you when you're going to get there just because of that technology. And we almost didn't get it. It was used for defense work, and it took some lobbying and insight and some resistance, in the name of secret information to protect ourselves, to get it opened up to the public. Now there's satellites that not only the U.S. has, but China has a constellation of them. Russia does, and India does, and the smartphones use multiple of the arrays now to get very precise timing, in addition to timing that they get from triangulation to the cellular phone towers. Then moving on forward, we've got Charles Babbage and the difference engine. He designed it in 1849, but it really didn't get built in 2002. And if you're ever in the Science Museum in England, if after you go over and either before or after you go over and see Greenwich and see the clocks, you can go to the Science Museum and see the Babbage machine that's been put together. It's pretty interesting. If everything's it's a decimal computator. It's all mechanical, and it does everything by subtraction. So it's a marvelous piece of equipment. And then there's more, but we won't go into detail on a lot of these, but kind of leap through from mountaintop to mountaintop about what came along to get us to where we could get these EAA telescopes in place. The vacuum tubes, Fleming and all that in 1904 started out radios, but then they got repurposed into digital computers with diodes with Arthur Dickinson in 39, and then the transistors came along with Barton Britton and Shockley in 47 at Bell Labs. And then lasers came along in 1960. The first ones cost about $50,000, but within a few years you could go down and test drive a car and get a laser pointer that you use as a cat toy free. And so you talk about technology getting adopted quickly. And the neat thing about lasers is that they allowed you to just send information and also to do sky tours, another byproduct, in either green or blue or red. Then Seymour Cray came along with supercomputers in 1964. I joined his company and worked in their research labs, where he was instrumental in 1973. And then that's where I got my start in my profession. I'm not an astronomer, I'm a computer scientist. Then personal computers came along with Blankenbaker in 71, the Kim 1 and the ones like that. And Robert Metcalf was a grad student at Harvard. Just a second, I need to swallow water here. And he proposed to do his doctoral dissertation on a way of communicating that later became known as Ethernet. And his committee kind of laughed at him at Harvard. They said, no, you need to do something more academic, and this doesn't make sense, and yada, yada, yada. Anyway, they didn't like his new idea. So he wandered down Mass Avenue there in Cambridge, Massachusetts, and pitched what he wanted to do to the folks at MIT. And they said, that's really neat. Why don't you do that? And so Harvard lost him, MIT got him. And then he went on to invent Ethernet. He went on to start a company that started modems, and they later made the chips that go in cellular phones. And the first protocol that was used on Ethernet was XNS, for Xerox Network Services. And he ran Xerox PARC, which was the Palo Alto Research Labs, which was next door to Control Data, where I was later working. And that's where Steve Jobs and Wozniak went over and saw the computer with a mouse the first time. at Zero Park, and that's what introduced Apple, which introduced the iPhone, which is one of the key technologies that helps with these EAA scopes later on. And then the routers came along in '75, and BitNet came along with RF Fuchs, and that was funded out of DARPANet. And I was running a lab at Control Data then, and we piggybacked on BitNet and became the second commercial entity that did networking back in 83 or 84, right around in there. And then the internet standard that was adopted by ARPA happened in '83. Then Tim Berners-Lee at CERN did the World Wide Web in 1990, and then the Internet of Things was conceived and is still evolving. So all of these were things that shoulders of people that did this stuff that people stood on to bring things forward to get to where we are in EAA astronomy. And so at the end of the 20-teens, around 2014, I believe, Unistellar was formed in Marseille, France. And a few years after that came the EAA Kickstarter project. And what made the Unistellar scopes different was all of this innovation. They had internal hardware. They had a Raspberry Pi 3A that they put inside. They had a custom board that sat on top of it. And they just got a stock Sony IMX 224 camera sensor. That camera sensor is a color sensor. It does have a batter mask on it, so it sees red, green, and blue, which is the same your eye sees. But it also captures photons well into the infrared spectrum. And then they put a 16 gigabyte micro SD card in there. And if you want to get more technical insight into this particular thing, you can go to GitHub and do a search for Jan Kaiser's reverse engineering notes on GitHub about how he's gone into the software and shows the different pieces that go together that make an EAA scope work. And you'll see that's parallel to a lot of utilities like SharpCap and Nina and things like that that are used in more traditional astronomy. So Unistellar was followed by, and almost parallel with other EAA telescope vendors, and here are some of them that are available. The Dwarf Labs has had a couple of scopes out there, up to the Dwarf 3 now, which is about $500. And Unistellar has the Equinox 2 that replaced the Equinox 1, and the EV scope was the original one. The Equinox 1 and the Equinox 2 have smart eyepieces on them. It's just an eyepiece that looks at a little LCD screen. The original one was one that they just kind of cobbled together themselves. And in the Equinox 2, they took a product that Nikon uses in microscopes for enhanced imaging and microscopes. And they just take the data that comes from the Sony sensor that transmits it to the smart eyepiece that Nikon has. The eyepiece is $2,000. So they marked it up $2,000 and 10%, and that's the EV scope 2, which is $4,900. Otherwise, those two scopes are identical. And then Vayanis had the Vespera, which is about a $3,000 scope. It was very similar to the Equinox and the Dwarf 3, or the Dwarf early ones. But they said, there must be some high rollers out there that really want a really fancy EAA scope. So they announced the Hyperia. It'll be a while before we put this into the NOVAC loaner scope program. I'm sure it won't be in my lifetime. We'll have to wait for inflation to catch up on this one, to where we can afford it. But they think, I don't know if they've sold one yet or not, but a couple of years ago, they announced a $45,000 one, and I'll show you some tech specs on it in a few minutes. And then ZWO came along a few years afterwards, and they came out with the SeeStar 50 for $500. And then about a year after that, they came out with the SeeStar 30 for $350, which has been price adjusted up to $400 with the tariffs. And then Celestron came out one that is sort of an EAA scope. And unlike it, the Celestron Origin and the Vayanis Hyperia are not as portable. The Origin is about 55 or 60 pounds to haul around, and the Vaonis Hyperia is, I think, 100 pounds or something. You know, it's big, but it's a smart scope. All the rest of them are things that you can haul around, you know, in the back seat of your car. A lot of them you can have in a dorm room, and we'll look at some of those now. Those of you who like data, here's a chart that I put together of the current EAA scopes, and there's the weight in pounds, the price, the optics that are in there. And it's interesting, if you look at the optics, the Equinox scopes are Newtonians, the ZWO scopes are apochromatic refractors, 3-element ones with ED glass, and Celestron Origin is a RASA, and then Vespera and Vaonis have 3-element APOs. So even the $45,000 one didn't get extra elements. It's a 3-element one. And there you can see the difference in the focal lengths of them. They vary from the SeeStars is, I'm sorry, this is the aperture, 30 and 50 millimeters and 114 millimeters. The big daddy on it, which accounts for all the weight, is a 150 millimeter aperture on the 3-element Vaonis. And then the focal length also varies quite a bit. The Vaonis has over 1,000 millimeters of focal length. The Vespera Pro has 250. The Origin's 335. The others are in the 150, 250 range that are the refractors. And down, kind of singled out that's a little bit different, is the EV scope and the Equinox. They're identical except for that eyepiece. One has a smart eyepiece. The other one doesn't have an eyepiece. And they're both 450 millimeter Newtonians. The other thing that varies is the F ratio, the you know, the speed of the light, which is a function of the focal length and the aperture. And so the EV scopes are, excuse me, f4.3. The SeeStars are both f5, and the Dwarf's f4.3. The Origin is very fast. It's f2.2. That's the RASA type telescope. And the Vespera Pro's f5, similar to the EV scopes, and the Hyperia is f7, which isn't all that fast, except it's over 1,000 millimeters. So that is fast for a, you know, one of that size. The other thing that varies immensely is the sensor that's used in. These are all Sony IMX sensors. We're not going to go through the stack on this stuff, but this thing will be published, and you can grab this data, you know, off the YouTube channel that we've got. And there's all the data of what sensors are in each one of these. And rumor has it that the SeeStar S30 Pro is going to have an even better sensor in it. But the sensor doesn't matter as much in these scopes as it does in more traditional scopes, because when it's integrating, even if you have a low number of megapixels, like in the SeeStar, you only have 2 megapixels there. You know, in the EV scope, you have 6.2, which is 3 times as many if you only take 1 exposure. But if you take 15 exposures, which you do with the SeeStar, and you take 20 exposures a minute with the EV scopes, if you do exposures for 20 or 30 minutes, you have tons and tons and tons of megapixels. And so it isn't as critical. The more critical thing is how you suss out the signal from the noise in finding out the pixels that you're interested in versus the pixels you're not interested in, like all the pollution from the moon, if you're not looking for the moon. Otherwise the moon isn't pollution, or all the street lights and the amp glow and all the light pollution that you get from the cities that are around. So what makes these telescopes different is innovation, actually. You know, all of them are standard optical scope designs, and they have a bunch of electronics piled on top. And if you look back to Isaac Newton, you know, a great quote that I just love is, "If I've seen further, it is by standing on the shoulders of giants." And the people that did all of these technologies that you see there below in that list is what made these telescopes possible. And the thing that really set them apart was, this is a plug for my profession, was software engineering focused on user experience. So what they did is they figured out with the person involved very intimately, how to do software engineering and integrate all of these technologies through systems integration into a turnkey package so that you could buy one of these things that will fit in a 23-pound backpack or fit in a 5-pound carry-on bag. Is two examples of these things, and of systems integration, and they're highly portable, and it has just opened up the hobby of astronomy immensely to people that never could afford it before. The price drop is $4,000 down to $350 and $400 to get started. The learning curve has dropped from a year plus down to 30 minutes, and the ability to house these things. You don't have to have a big garage to put it in. You can actually house these things in a dorm room, or in a closet in a condo, or in a townhome, or things like that. You don't have to have space for it. And so it's just made it both financially and physically and lifestyle available to people, which is just great. So we've got some time now for discussion, and I'm going to stop presenting. If I can give me a second here to get out of this. And let's see, I'm going to stop preview. Okay. And then if you want, I'll start monitoring the chat. And if any questions are popped up, or if you just want to pop in and ask questions, you can hand raise or post your questions over in the discussion side. Bill, go ahead.
Yeah, thanks, Paul. I don't own one of these. I may never own one, but we're always dealing with questions about them. And I appreciate your good summary there. I'm sorry about the echo.
You're fine. We can hear you loud and clear.
All right, good. Is aperture that important? I mean, scanning your list, the EV and the Equinox have a much bigger, for the $3,000 or less, they have considerably bigger apertures than the others. And I'm wondering, is that why they're priced a little more? I'm still trying to understand the relationship between price and quality, I guess.
It's there's not as much differentiation I found in them. I own 2 SeeStars, 2 of the Unistellars, and then I've got traditional telescopes, both. The thing I want to point out that I haven't pointed out yet is that if you get an EAA scope, you're still allowed to own a regular telescope. There's no rule that says you can't have those 2, and you're allowed to have more than one. Okay, so and so I think a lot of people have migrated to them for convenience. If you really want top quality and you want to do coffee table books of astrophotography, you definitely have to go the traditional route, and their aperture is king. If you get into the EEA scopes, I think the limiting factor isn't aperture as much as light pollution, is my experience, and just how long you have to integrate and how good the algorithms are. It's and how good the sensor is, more than aperture, because you're stacking there with the realms of where you are. If you really want to get out of it, you get up to the one outlier, which is the Origin, which is a 60-pound telescope instead of a less than 20-pound telescope. And so for 4 times the weight, you do get a boost there. George has, and several other people have the Celestron one, and they get better results from it. But
so the main driver of cost is not necessarily the aperture; it's the processing, the electronics, right?
It's both to an extent. I think there's more. The cost to build the software is astronomical. It probably dwarfs everything else. Optics have gotten so cheap. You can, people used to hand grind optics, to suss out better stuff. And you can buy really decent optics with ED glass and all of this stuff, for under $20 and $30. It's just unbelievable how cheap optics have gotten. And of course, you get past a certain point, and you get more aperture size wise, more millimeters, then it gets expensive. You're not going to get a 3-meter mirror blank cheap, those sorts of things. But if you're down in this 5, I don't know, 2, 3, 400 millimeter stuff, it's pretty cheap there. But the software cost is huge. And then the gating factor on that is how good you market it. The first one costs you a fortune, millions of dollars. The Kickstarter project for Unistellar was the most funded project in the history of Kickstarter. It set the record.
Oh, wow.
And it took them 4 years to get that thing out, 2 years longer than they wanted. And most of that was software integration costs. So that a lot of people, especially those of us older people, don't realize how much software integration costs, because we're so tied into what it costs for the optics and also on the motors. The other thing that I didn't talk about that really set this apart is being able to buy servo motors that cost $3 and $4 a piece, instead of getting the motors that the gears are the key thing in the motors, getting these worm gears that are ground down to millimeters, and with expensive CNC machining and all that. And if you, like, I started out with the Losmondy G11, and the first option I had to make the Losmondy G11 was to pay O-Vision $600 for a special worm gear to put in the thing. And all that did was have this Gemini thing that had no human engineering in it, this computer go find objects to, for the Losmondy G11 to track. And then the periodic error correction was just awful in the thing. And so what they did was you take these EAA scopes, and if you can't see the North Pole, that's fine, because you don't have to polar align them. You just set the thing up, and if you can see 3 or 4 or 5 stars, you just have the sensor look at it. The sensor sends it to the Raspberry Pi. The Raspberry Pi says, oh, I've looked at the geometry relationship of where these stars are. They're unique. And so I know, because I know from the phone and the tablet, the time of day, the elevation, the latitude and the longitude. So having those pieces of information, plus the geometry of where these stars are, I know exactly where I'm at. And I know where you want to go, because you picked it out of the memory table that it's already stored in my memory. So you want to go see the Orion Nebula, and I'm not there. I'm 50 degrees away from it. So I'm going to tell these servo motors that I paid $6 a piece for to move over to the Orion Nebula. So it whirs and it goes alt-az over there. Or it does EQ if you do take the time to polar align it. You can do either one on most of these scopes now. And then it gets over there, and then it looks at the stars again, and it says, well, I tried to get there, but I'm not there. But I've got new stars, and I know where I'm at, and I'm 85% of the way there. And so I'm just going to try again. And so it does another iteration. And with 3 iterations, it's got it dead center with $6 motors. That's amazing. The other thing that I found amusing on this, back in around 2016 or 17, I think 2017, when this Kickstarter program announced, and I sent them $2,000. I said, if you can pull off what you claim you're going to do, they had the usual marketing hyperbole. It says, oh, this telescope's going to be X times 1,000 better than what you currently have to find stuff in light polluted areas. And I said, if they can make a dent on this, and it can get me out from the pressure of this Losmondy G11 that I wore out on and sold, I said, more power to you. And if I lose the 2,000, at least you'll get us down the road. And so I posted something on the listserv in NOVAC, and you wouldn't believe the blowback I got about a bunch of about people judging this as a huge scam. It was totally impossible. Why on earth would anyone want to look at something that came from a sensor? They can just, go on the internet and look at pictures of the Hubble, blah, blah, blah. Totally missing the fact that people still do enjoy going outside, and they really, really get a thrill out of owning a piece of equipment that can actually go find things for them, and finding more than just flipping pages in a coffee table book. They can take a device, a mechanical device, and let it find things. and enjoy the outside and enjoy star parties and that kind of stuff too. So that's kind of what happened there. And I took it to a Stargaze, and I set up from my good friend Dan Ward, and he was over there messing around with his telescope, and I was messing around with my EV scope. And in about 10 minutes or 15 minutes, I had a crowd gathered around looking at a nebula. And about 35 or 40 or 50 minutes later, if Dan's on, he can defend himself. He came over and he said, you know, I see what you're talking about now. He'd been one of the ones that had criticized me on the NOVAC website. So he went home and had his wife look at a YouTube video that I did about these things and said, you can get one of these. And so he's a zealot now. And we've got a whole bunch of people in the club now that have both, and there's a good spot for both of them. They really both have great things to have if you're an astronomer. Okay. Any other hand raises, or let me go over and look at the chat.
Hey, Paul, can I put in my 2 cents worth?
Sure.
Okay. I was starting out on the traditional route, essentially, get an 80s SCT and go up to Sky Meadows. You were the one who effectively told me, go this route. Kind of going, I already bought this one. I bought this much. Do I need to go this route? So I ended up borrowing the S50 on the loaner program, and I finally had to decide, you had a point. This will actually work. So what I ended up doing was that I ended up buying one and upgrading it with all the accessories I think I would need, because as it is, it'll work on the out-as mode, but if you want to go for long-term imaging, you need to go equatorial. So bought all the accessories, that puts the batteries to do a whole thing, and actually able to get images that will almost be what you call for green sea. So I found that we need about 10 hours time around here. That's essentially the way we're going to do it. So for 10 hours, okay, that's decent. All we got to do is either stay 2 nights out straight and just image, or you can do it the other way. My second one, the imaging time in half. So this is essentially what they would call the gateway drug for astronomy. The price is essentially hit the sweet spot that someone can pick it up without any prior experience. Go out, set it up 10, 15 minutes, and then within 20 minutes you probably get a decent shot. Now, whether or not to go to the next level of that, not learn to fix inside serial. It's another issue. It's another skill wall to climb.
Yeah. I think some of the pictures that I showed at the beginning of my talk, there are people who have sussed out beautiful, award-winning pictures out of these things also. And the accessories that you mentioned, ZWO sells if you want to run it equatorially, you just click a thing in the interface, but you need a wedge for it, and they sell a wedge for $71. So it's the accessories aren't real expensive. If you already own a tripod, it's better to use it than the little tabletop tripod, and it just takes a 3/8 standard tripod bolt, and you can spend some money for a better carrying case. Also, if someone's, to me, the big difference if you're going to go to the ZWO route is to get the 30 instead of the 50. You lose a little bit in one area, but the thing you gain is a second camera. It has 2 cameras instead of 1, and the second camera allows you to find objects much easier if you want to use it. One thing I didn't mention is it also works as a terrestrial camera, and so if you want to have a what's equivalent to a 35 millimeter 1300 millimeter 1300 millimeter lens, you can have for $400. And if you're not taking pictures of fast moving objects, you can do landscapes and things like that. with a SeeStar S30, but you need that second camera that's in it to be able to guide it. With the 50, you don't have the second camera, so you don't have a wide field, and so it's like looking down a soda straw to guide it instead of having a real wide field of view. So if you're going to do terrestrial photography, I would also go to the S30. And if they actually release the thing next month and you can get it in the next 2 or 3 months, you may want to hold off, for a month or two. But I'm sure glad I didn't hold off too long, because I've gotten more use out of the EAA scopes I've got than the other 5 traditional telescopes combined, just because of the convenience. Never before are you able to sit around the dinner table and say, with guests, say, hey, have you ever seen a globular cluster, or have you ever seen a, whatever space object you want to look at? Said, if you want to, we can just walk down to the church parking lot 4 doors down from my house and set up a telescope and look at a nebula. And they go, oh yeah, that'd be cool. So we shag down there and take 15 minutes, set up and look at Orion or whatever is up. And then maybe say, do you want to look at anything else, or is that enough? And if they want more, you can do it. If you don't, you can take the thing down and you've done 30 minutes worth of astronomy that was impossible before. And then if you want to do tons of astronomy, you can take these scopes and you can, I didn't mention earlier, but they've been made alpaca and ASCOM compliant. And ZWO has built in that interface. It's still a little bit fragile because they just did it recently in the last month or two. But if you want to set the thing up out in if you've got horizons in your backyard, you can set it up in your backyard, and you can fire up your laptop inside with Nina and go through alpaca and ASCOM and program 3 or 4 objects that you want, and go to bed and get up the next morning and grab the stuff and bring the telescope in the house, plug in a USB-C cable, and then suck the thing down into your computer and do PixInsight for the next 3 months, making the thing beautiful. That's exactly what you're doing, if you're capturing 50 hours or 500 days or whatever of these other objects with others. So that's, it's just amazing what you can do. So you can suss a lot out of them. They're more than toys. And there's a lot of growth in it, but the learning curve is steep if you want to get down in the alpaca Nina route, or if you want to go over to Cyril or those types of things, if you want to run it in EQ mode other than Alt-Az mode. But if you just stick to the basics of it, you can have a lot of fun with your friends and relatives, and you don't drive them crazy, with astronomy minutia, and they can join you, in outreach and that sort of thing. And the place where they really shine is outreach. Especially the Unistellar ones, and I hope SeeStar puts this in theirs. They'll support up to 10. They support 1 operator and 9 observers. So you can have 10 people sign on with their smartphones or tablets at a time. And then it allows all of the observers, while they're observing, to use text editing and emailing. And right when you're out at Sky Meadows, you can just say, hey, you can just link into mine and follow along. And if you want to text these to your friends or email them to your friends, they just do it in real time, right while they're watching the photons collect up on the screen of the operator's iPad. They do it with their Androids and their iPhones. So it's things like that you can't do with telescopes and outreach that really hit a button. And the other thing is it makes outreach possible even in rainy and cloudy days. We can go set up, and we have just as much interest in the equipment as we have the sky. People are really fascinated with 2 things. Those of you who are astronomers don't know how rare you are, and you're just like rock stars to the public, and people really get off saying, oh, I get to talk to a real live, honest to God astronomer, and they're going to tell me about their equipment. And if I have some desire to be an astronomer, I can learn from them and find out what they have and what they do and who they are and what they're about. And then they can show me, even if it's completely clouded over, all of these images that they got last month or 2 months ago that we would be looking at if these silly clouds weren't up there today. And you can have the stuff whirl around and, and drive it with your thumb from a smart device and all of that. So those are things that make this really good for outreach. Okay, George, you got something you want to?
Yes, first, weight, I don't think for any of these telescopes, the weight is a real issue. Like the Origin is a heavy telescope, but you can take it apart into 3 pieces. The tripod is 14 pounds. The mount itself is 17 pounds, and the telescope, the OTA, is actually 10 pounds. I can carry all of these with one hand, and I'm 83 years old. So it's going through it all at once. And they all fit in the car very easily. The other thing is Bill Barton talked about aperture. Aperture is still aperture, isn't it? I mean, the bigger the optical surface, the more resolution you're going to get. So if you compare the resolution of, say, an 80-scope 2, Equinox 2, say, with a SeeStar, I think we ought to do that and see just how much different the resolution is. But it must be better, I would think, with the bigger aperture. 4.5.
Yeah, the limiting factor though is the integration time through the wavelet algorithms that are in the Raspberry Pi.
Yeah, you can take with I usually show about 10 different objects to people and outreach events. I just go one for the other because in about 2 or 3 minutes I can get a decent image. And in fact,
you're right. It's the front end that helps you though. The aperture helps you tremendously on the front end.
Yes.
But you can have all the aperture in the world and all of them time out at about an hour. And so you can collect photons and integrate with the small aperture stuff. And if you have slightly bigger, it just gets there quicker. But they all top out.
Yeah, that's true. Yeah, but still, you can take really quick. Like you showed the globular cluster M13. I took a look at my Unistellar stuff, and I see I got a beautiful globular cluster image in 2 minutes. So you can show one thing after another. If you wanted to just explore, say, galaxies, so you have a pocket sky atlas and you see all these galaxies, you can, in 15 or 20 minutes, get decent images of all the objects. You don't need PixInsight or anything to see those images. They're good enough with just the Unistellar. So if you're not, I think these telescopes are made for people who weren't going to be astrophotographers, the real astrophotographers, and take the images that take weeks to get or months to get, and they put it all together. They were made to be quicker, and if you just use the enhancements on your phone or your tablet, you can make a beautiful image. So you want to make it better, you can do what the one guy did with the Orion Nebula and use PixInsight, spend a lot of time doing it. But if you want to start using all those fancy stuff, why not become a real astrophotographer, and then you can make these images that take months, whatever you want.
Yeah. Well, if you got $4,000 instead of $400, you can get the Edge or the Celestron one. It's 10 times more expensive.
Yeah, I saw you can take images with the RASA optics. They sell that telescope alone. You don't have to buy the Origin. You can buy the 6-inch RASA telescope on the optics of it and put your own cameras on the end of it and do what you want with it. You can
write your own software.
Yeah.
Let's take a couple more questions. We're kind of at the end of our time here. Let's see, someone asked about filters. Most of them have a pollution filter in it. The SeeStar has autofocus in it. I think the Dwarf has autofocus too, if I'm not mistaken.
Yes,
it does.
Yeah,
the Unistellar doesn't. A lot of them come with solar filters. With the Unistellar, you have to buy the solar filter. There's a dew heater inside the SeeStar.
The Unistellar Odyssey models have autofocus.
Oh, that's right. Right. Yeah. And so there's, so there we go. Any other quick questions before we sign off? We've kind of at the end of our time allotment here. Well, thank you all so much, and look forward to seeing you at the different events, and hopefully we can get back to, George Mason University and meet in person and have the dinners afterwards. All of you have a good holiday season, and we'll see you next year. And if you haven't voted yet, do vote so that we can make everything legal for the club for another year. So this will end it now. Good night, and best wishes to you all. Bye-bye.